Hi. Today we'll talk about calibration in recommender systems, specifically the ranking layer. We'll talk specifically about calibration and not in general about bias. Calibration means the estimates that are coming out of your ranking layer, uh, have the same distribution as the observed event. So it's closer to a probability, which is what uh, you hope that is coming from the ranking system. We'll also explain why it is often overlooked and what is the benefit of making a ranking system calibrated. But before I dive in, I just wanted to give a shout out to Marc Ferradou. He's my co-author in this article. He just out of the blue, he reached out to me on LinkedIn and he shared his knowledge of this field, which he's collected over many years, and I'm sure over many failed experiments. So I really appreciate that. We kind of jointly wrote an article together, and that's what I'll be talking about today. Like we do normally, along with this, we've also shown how to implement some of these ideas. There's a GitHub repository. I'll link it in the video and the Substack post. But I'll give you an overview of it. As usual, it has the implementations, it has the tests pass, and it is similar in style to our previous repositories in ranking. Okay, so calibration is about the estimates that are coming out of your ranking layer. And let me be a little more grounded here. Normally in a recommender system, you have a candidate generator. You could have many candidate generators. And then the candidates coming out of them, you sort of merge the duplicates. Then let's pretend there's one ranking layer. It doesn't, the same ideas will hold if you have an early ranker and a final ranker. But the ranking layer actually is split, in most modern recommender systems, it's split into two parts. One part is the estimator. So for all the candidates that you have post merging, this layer comes up with an estimate of various tasks, various events. By the way, if you want to learn more about this and the complexities of multitask estimation, there's a very nice video by Andrei Karpathy. Let me just show it to you so that Andrei Karpathy, multitask estimator. Yeah, well, this one, Tesla Autopilot multitask learning for perception prediction, goes into the second layer complexities, and you learn some of his rules of thumb here. Okay. So coming back, your ranking system has actually two parts. One part is this multitask estimator, and then there is this selection stage. Like a conventional understanding of ranking is, we will look at items and he will have one process that comes up with a ranked list. That is not generally what practitioners do now. Nor currently, the most modern recommender systems have this two-step process, which is an estimation and a selection stage. So today, when we talk about ranking, we are primarily talking about this estimation stage. Let me ground it in an example. Imagine you're building a podcast recommender system, and you think it's important for the business to see that, like, when you offer a person to follow or subscribe a creator, how often do they do that? And based on that estimate, you will provide suggestions to the user. Okay, So this becomes a task of your multitask learning, which is to follow or not, right? Or subscribe or not. And then you get data from that and you improve over time, and hopefully that loop kicks in and your recommender system improves. So this estimation layer is what we're going to call the ranking layer today. Like I mentioned, for each item you could have multiple tasks. You generally have multiple tasks. In the podcast recommender system, it could be, did you subscribe or not? Did you maybe you clicked into that creator, and like there's a profile icon, and you can click into it, and then you can listen to a podcast. So did you click or not? After clicking, did you listen to the podcast or not? Did you like them or not? Did you share them or not? So those are various measures of what value the user derived. And then there are the downstream value measures, which is, did you come back and listen or not, and things like that, right? Okay. So from all the items, you compute task estimates, and then you have the selection stage, which results in a small selected set of items. It's actually not just a small set of items. At the last layer, it's also the ranked list of items. So the specific order in which the items, so it's not just a selector, but it's also a list creator, if you will. Okay. So this is what more often than not is the architecture of a ranking system. So what we are talking about is this estimator. So let me specify a little bit more. We need to understand this, because this is why when we say that we need calibration, we want to know the internals of the ranking system so that you can understand what is the API or the contract between multiple layers, and why calibration can help in that process. So for each of your candidates, you come up with estimates. Then you have some sort of logic that combines various estimates into one final score. This logic is what we are calling the value model. There's this very nice paper, multitask fusion, which I think is a better, more technical name. Multitask fusion. Value model is more like an industry term. But I recommend you guys to read this paper, Multitask Fusion, via reinforcement learning for long-term user satisfaction. Okay, so coming back, this multitask fusion combines various estimates into one final score. This is what we sort and select and rank on the basis of. Okay, so what we are going to talk about is today, what we mean by calibration is that the estimates produced for each candidate, that should be calibrated to the observed probabilities of those events. Okay. So the estimates produced should be calibrated to the observed events. Now, do we really need that? Do we really, let's say the probability of going back to the podcast subscription recommender, suppose we show you, I'm building an app, I show you options to subscribe, and let's say in average, users subscribe with a rate of, let's say 5%. But somehow the scores that are output by my model is 20% in average. So maybe for some options it is 23%, some options it's 17%, some options it's 5%, and we rank and show you a list. That still works. As far as the output is concerned, once you have a final score, once you have an estimates and you combine them into a final score and you sort them, you don't really need these estimates to be of the same scale or distribution as your observation, right? And that is why often people building recommender systems have not focused on calibration. They have not spent like ranking cycles or even development cycles in ensuring calibration. Because the thing works without it, the feedback loop works, everything. So what does not? We'll come back to that, but just want to make a small detour. There are, though, many situations where it is a P0. The first thing, if you kind of search, the first thing you'll hear about is ads, because in ads ranking, the probability of the click or the eventual conversion, they are used in pricing the ad, the actual money that the advertiser has to pay. So there, it's a contract between the advertisement platform and the advertiser. So there, it's kind of high priority. Okay. So more in general, we are talking mostly about in general recommender systems today, because as we anyways have to have calibrated models. So in general recommender systems, my claim is that we should ensure that the estimates coming out of our ranker are calibrated, and we should ensure that there are many axes of calibration, and like you should kind of look into what makes most sense for you in your business. So we'll go to that. The main reason why I am encouraging you to consider this calibration is that the value model layer, or this multitask fusion layer, that's a separate process. And that assumes a certain scale. Like, let's say you have two events. One is that you will subscribe to this podcast creator, and second is that you will listen to a podcast that's on their profile page. Both are good things, both as far as a podcast app, both of them deliver value. And let's say your value model, you trained it and you assigned a score of 0.3 to the first one and 0.7 to the second one. Now, if for some reason tomorrow your estimates of the first event become twice, even though the relative order of these estimates might be the same for different items, different podcast creators in this case, even though the relative order is unchanged, if the scale changes, your rank list will change, because the value model has a fixed weight for that event. And those weights have been tuned separately. Now, could there be another system which sort of adjusts constantly? Yes. But in practice, you want some sort of decoupling or some sort of clean contract between your estimation and your value model, because it enables faster development. It enables your experimentation of value model to only worry about the value model and not about the ranking layer. So it's kind of a clean contract if you ensure that your ranking model is calibrated. What I call it self-calibrated, in the sense that it's calibrated across revisions. Like the new ranking model has the same distribution as the old ranking model, and the best way to do that is just kind of ensure that it's calibrated, that the new ranking model is calibrated to the estimates observed in the data, and the old one was also calibrated to the estimates observed in the data. Okay, so by now we have been talking about calibration a lot, and by the way, there's some code examples in all of these. They'll explain what we mean. We've been talking about calibration a lot. Let's go into the different ways of defining calibration. So one is, for each task, the average value of the predicted probability of the task should match the average value of the observed probability. So in average, like let's say you build an estimator, and then you take a day of values that your estimator came up with for each task. And on that day, you see what is the observed value of that label, of that task. And roughly the distribution should match, at least in the mean. So that's what we are talking about in this definition. Second is, if it's possible that your model is overall calibrated, but it still over predicts or under predicts and some ranges of the prediction. So let me explain. Let's say you again take 1 day of data, that this is what your model estimated for a task, and this is what was observed for the task. Now remember, your estimation is going to be in the 0 to 1 scale, whereas the observed label is going to be 0 or 1, in case it's a binary label. And what I'm suggesting we do here is, and there's a lot of, just an old concept, there are very nice papers of it. If my explanation does not make sense, please search ECE, calibration error. There's this paper by Killian Weinberger et al. From 2017, I think, that I really loved in this space. Okay, so coming back, you take the day of data, take the probabilities the scores that you estimated. We wish they were probabilities, but we don't know right now. For it to be a probability, it has to have the same skin around that. So take the scores that it estimated, then compute equal sized bins. So, like you do for a histogram, compute equal sized bins. And here I'm saying, let's say the average prediction in each bin, average for the 0 to 20th percentile is this. Average bin in 0 to 40th percentile is this, etc. And then for each bin, you also see what is the average value of the user label. Okay, so for each bin, you hope that the average probability, score that you estimated is similar to the observed probability. Because if that's not the case, like it isn't here, it means that for very low values of your prediction, it's actually the true event, the actual event, has a higher likelihood of being 1 than what you're predicting. Similarly, for in this range, you're over predicting the probability of being 1 or true. Like the average prediction is higher than the average user label. So it's clearly the distribution of blue is more extreme, so to speak, than distribution of your observed label. And this is what you might want to change. Why? If you go back to, again, our system that we are combining multiple estimates through a value model. Now imagine you have, again, those 2 tasks, right? The probability that the user subscribed to a creator, and second is they listened to a podcast on their profile page, right? It is possible that for one task, you are here, and another task that's in the highest percentile, but maybe the calibration for the first class, the first task is under calibrated in this zone, and the second task is maybe under calibrated in this zone. So you're going to be calibration wise unfair to that task, because your estimation is not correct, not what is the right scale for that. As opposed to that, and your value model doesn't know, it just has some weights, 0.3 for the first task, 0.7 for the second task. It just assumes that the scale that is coming out of your estimate is the same as what is the observation. So again, the problem is that your estimates might be relatively correct, that when you estimate, hey, creator 1 is better than creator 2 according to task 1, that might be more generally correct. And same for task 2. But since the scale is not correct, it is possible that you are the final ranked list is incorrect, because there is this value model in the middle, a multitask fusion layer in the middle, that assumes a certain calibration for your model. Okay, so first one, we talked about overall calibration, that each task should be calibrated throughout the day. Second, we said that let's ensure that even the buckets or the bins for each task is calibrated. Besides overall calibration and calibration on each prediction bucket or bin, which is the second level distribution, another form of calibration that you could be interested in is calibration per user cohort, or more in general, for various values of a feature. It's actually quite common. For instance, let's say you build a podcast recommendation system. Let's go with that same example, and it's a global application. And maybe if you look at all your data, you find that only 5% of your data is from a US audience. And let's say for business reasons, you care about being fair to the US audience, fair in the sense that the value model should not be miscalibrated to this US audience, right? So you want to make sure that the estimates coming out of your ranking model should be such that, in general, for one cohort, let's say in this case the US audience, it is of the same scale as the observed probability. So let's say you create a feature which is, for each user, this feature is 1 if this user is in US and 0 otherwise. Of course, you can see how it will generalize to, you can make to country groups, or new users versus experienced users, or users who have already a lot of subscriptions in this podcast ecosystem, or not. Like, you can make various cuts of your user space. Also, the item space. You can also look at calibration on the item space. I think the same machinery applies. So if you have a feature which is 1 or 0 for among your training data, then what you can do is you can, the same idea that we had here in terms of bins, you can look at that in terms of 2 bins, the feature with the one bin having feature value 1 and the other value 0. So if you go back to our motivating example of podcast recommendation, and we want to do a fair job in terms of calibration for the US audience, then the feature we had in mind was the users in US equals 1 or 0. Then what you can do is observe the average value of your estimates for a long enough period, let's say a day or a month, etc., and see if there's a discrepancy between your predictions and the observation, both for the bucket feature equals 1 and for the bucket feature equals 0. Okay, so these are 3 motivating examples we have talked about, and you can talk about more. I'm going to go after this to prior work, but I think for I do that, I think these are very relevant questions for business. Often when you have built a ranking model, a lot of time is spent in understanding if there are gaps in it. And gaps are often of the nature that, hey, we are in general doing a good job and we can keep investing more in model architecture and, like more data, etc. But I feel like we are not doing a good job for new users. Feel like we're not doing a good job for new items. I feel like we are not doing a good job for um, users who have very less connections, or like there you could. This is a normal um, misalignment that happens between areas of reduced importance of the ranking model due to artifacts of the training data and what is important for the business. So you can get ahead of that conversation and say that, hey, I have proved and I have built in structure to ensure that is always the case, that my model will be calibrated to the cohorts of importance. Not only will it be like even if it's a small cohort, like not only will it be calibrated to the dominant cohort, but even to the cohort that is 2% of my training data set by construction, and we'll talk about how, but we have ensured and we can measure whether our estimates are calibrated. And why does that matter? Because we have a value model on top, which assumes a certain scale, and most of the time the value model is the same for different user cohorts. It's actually very costly, both in experimentation time and in terms of top line metrics, because it's very hard to optimize. So generally you have the similar and or same value model for all user cohorts or item cohorts. So being misaligned for a certain cohort can be very costly to the business. So I mean, if you want to take one thing from all of this, is that the areas that are important for the business, make sure that your estimates are calibrated to them. Okay, so that's the calibrated per user cohort idea. Okay, before we go to implementations, let's go to prior work. Yeah. So in most classical approaches, calibration is often applied as a post-training step. And here we point out one example where they leverage the idea of using a calibration model to improve the reliability of probability estimates. In this case, they use temperature to do the calibration. So temperature is specifically in certain settings, you have like once you have created the logit, you can kind of divide it by a temperature and then compute the sigmoid. An advantage of this method is that by using an independent data set, it should kind of generalize better to new data. But of course, the disadvantage is that it's additional complexity. You know, there's a paper that we recommend you to read. A loss function approach, where they explore how having a scale calibrated multi-objective loss function can not only allow you to increase calibration, but also benefit your ranking score in a list-wise manner. They argue that using a multi-objective, where one is for ranking and second is for calibration, is not always compatible. They prove that the common loss used actually pushes the gradient scores in a different direction. A layer. Another way to achieve calibration is by introducing a last layer into your network that achieves the calibration for you. This, 9 out of 10 implementations and ads, you will see this is what's kind of done. For example, LinkedIn created an isotonic calibration layer for the ranker, which helped increase offline and online metrics. This is actually very important. This is a production recommender system, like it's been trained over 10 plus years. And I think a lot of times when you're working in the industry, people look for what's the validation for the idea. This is a validation for the idea, that this helped them increase both offline and online metrics. And, there's a lot, like all of these are links to papers. There's a lot of depth in this that I recommend you guys to pursue, especially if you're a practitioner in this area. Which one to pick? It depends. And at a high level, what we are trying to communicate are the pros and cons of each of these. The kind of the simplest path to implementing and reducing all of these losses, the overall loss, the per bin loss is also called ECE, and we have some math here, and per user cohort loss. At a high level, we're trying to say that these are not very hard, very approachable, and we recommend you that if you're building a state-of-the-art recommender system, you should do this. Okay. So now let's look at some implementation suggestions. I have some stuff here. I was thinking whether should I. Okay, let's look at the code snippets here, and if need be, we will look at the GitHub code. But again, also the GitHub code calibration arc in ranking and TML. This is the VS Code version of it. We can look at that also, but let's see the snippets here. Okay. So here, the plat scaling option, you create weights and biases, one per task. And once you get the logits of your normal MTML, for each of those, you multiply by specific weight and add a specific bias. All right, this is what you'll find in 9 out of 10 implementations. That works. That works. How can you improve from there? So this is, I'm slightly more partial to this because I think these are the sort of errors that particularly creep up in a value model setting. This is also there. Yeah, overall calibration error is also there. And, you can look at that. This is slightly more prevalent and harder to observe. Okay, here we add a loss based on the second loss, the calibration needs prediction bin. So what we do is, imagine you have the UI logits that are coming from your normal ranking estimator. In this case, we are computing sigma out of it, and then we are sorting them. These are the indices, and then we are sorting the predictions. We are also sorting the labels. This entire part is to be able to sort the predictions and the labels, and then we will create bins of them, right? And then we will create bins of them. And then we will find the mean value of the prediction per bin and mean value of the label per bin. Now, this is a slightly optimized implementation. If I were to write a for loop or something, this would be easier to write. You take your predictions and your labels, and you can sort it by the prediction, and for then you can compute your equal size bins, and for each bin you compute an average of the prediction, average of the label, and then compute a MSE, a mean squared error. and that's a loss. I slightly try to do it in a way that is more efficient, especially in the GPU world. But the main idea is that if you go back to the setting, we are trying to create these bins, and in each bin we are trying to create the mean squared error between the average predicted value and the average user label, average observed value. Okay, and this is in the file prediction buckets. Let me look at it. Prediction buckets calibration. So the first one is plat scaling calibration. Second one is prediction buckets calibration. The part that I was talking to you was here. Once you get your UI logits, you compute a normal loss, the cross entropy loss, and then the sigmoid sort indices to be able to reorder both your predictions and labels, then compute the mean prediction and label per bin, compute a mean squared error calibration loss. Yeah. And the feature version of it, remember we were saying that, let's say your feature is true for US users and false for non-US users, and you want to make sure that your model is calibrated for both. So this is what we want. And let's assume that you observe the data and this is what the current state is. Then to go from here to here in feature-based calibration, we are doing something similar, that after we are computing the normal cross entropy loss based on the binary feature, we are computing a calibration loss which finds the rows in your batch where the feature is less than 0.5 or greater than 0.5, which is true or false. And then it tries to find the prediction and label in each of these bins, finds the mean, and computes the mean squared error. Okay. And the hope is that once you provide this loss to your final loss, and you have a hyperparameter, a loss weight, calibration loss weight. Once you provide this loss, then your normal model, then by backpropagation, your model will be trained in a way that it is calibrated. Yeah. Another approach is debiasing the model arc against a feature. So it's in the file feature bias capture. Here we are not trying to add a loss. We are adding a model architecture component, and you can see it in feature bias capture. And again, we have tests for all of these, so at least the dimensions match and stuff. Once you have the feature, here what we have done is have a very shallow arc. I think this is one layer, if I remember correctly. It is literally a linear layer which takes one feature and outputs the number of tasks. And once you have the logits from this bias, we just add it to the UI logits. So in other words, all we are doing is that we are seeing, based on the value of the feature, how much do we need to add or subtract to the logit to make the output calibrated to different values of that feature. So this is actually more. This does more than calibration. This is what I would say, capturing a sort of. It's ensuring that this feature, whatever this feature can capture, can maximally capture in your residual error, you do, because you're sending it all the way to the top. You're not it's not at the bottom of the arc like all other features where its contribution can be underrepresented. This goes back to Killian et al.'s paper, where they say that earlier when neural networks were shallow, then calibration was less of an issue. But now with the more sophisticated neural networks, calibration is more often models are not calibrated, and for this feature, whichever feature you care about as business, you are bypassing that and you're sending it all the way to the top. Okay. Yeah. So that's the end. So we talked about what calibration means, why it's normally not done, and then we talked about some different definitions of calibration loss. We talked about work and related work by others, how calibration has helped improve online metrics, and then we talked about the code. We did walk through the code, and then finally, we went into some of the implementations.